We're going to apply the first law of the energy balance to an adiabatic reactor. And this is a semi-batch reactor because we start out with our product, some product in the reactor, and we continuously add a reactant. We're given the heat of reaction and heat capacities. The heat capacities are constant and independent of temperature, so is the heat of reaction. It's liquid phase, and our question is, after 6 hours, what's the temperature in the reactor? We're adding a hotter material, and then we have an exothermic reaction take place. Because we're interested in the energy balance and not studying kinetics in this example, we'll assume the reaction is very fast, so that essentially as soon as A enters the reactor, it reacts. So we want to write down an energy balance in the form of there's energy accumulation in the reactor. We have temperature changing, different amount of material, and in general, that's due to the fact we have energy flow in, energy flowing out in general. For this, 0. We have heat transfer in general, but that's 0. And we have work. And these are all rates, but they're 0. So we're just left with the change in energy within the reactor as a function of time. Now we could write this as the number of moles of A in the reactor times the enthalpy of A per mole plus the number of moles of B and its enthalpy, where both the enthalpy and the number of moles change with time. Number of moles change because we're adding material. The enthalpy changes because the temperature is going to be changing. And these changes result because we have some flow rate, some molar flow rate, so the dot indicate a flow rate into the reactor, and the enthalpy of A into the reactor. So this is the first law. The thing that we want to keep in mind, nowhere in the first law is there a heat of reaction, but we'll see the heat of reaction naturally occurs when we deal with the enthalpy terms and we rearrange this. Now, because the reaction is fast, because we want to, in this case, just look at the thermodynamics, that means as soon as A enters the reactor, it's converted to B. So all A is converted as soon as it's in the reactor. So really my balance on the left side is the number of moles of B in the reactor at any given time, because all of the A has reacted to B. So this is our first law, and what we want to do is substitute terms into this first law. But before we do that, before we put in numerical values, we're going to integrate it so we can eliminate time, because we're interested in what happens after 6 hours. So I'm going to bring the dt and we integrate from 0 to 6 hours. And so if we look at the right side, the flow rate in is a constant. So that's the rate, that's per time. The enthalpy in per mole is also a constant because the temperature is constant. So all I have is T. So I have the integral of dt from 0 to 6. The left side, I start out with so many moles in the reactor. They have an enthalpy, and I end up with a final value, and they have an enthalpy. So I could put a small f here to indicate final value. Of course, integrating this derivative and substituting the limit just says the final number of moles of B times the enthalpy final, which is a function of temperature. The initial number of moles of B times the enthalpy B initially is equal to this molar flow rate in, enthalpy in, times 6, because we're interested in what happens after 6 hours. So let's look at the various terms. The number of moles of B at 6 hours, well, this is just, we originally had 100 moles of B. In the problem statement, we're adding 15 moles of A per hour, and that converts to 15 moles of B per hour. So 15, and we do that for 6 hours. So this is 190 moles. That's the value for B. The enthalpy final, well, we're going to write this as the enthalpy of B at the temperature final. So the parentheses here means evaluate at this final temperature. Number of moles of B initially, 100. And the enthalpy of B initially is the enthalpy of B at 50 degrees. The flow rate in is 15 moles per hour. Enthalpy of A coming in is the enthalpy of A evaluated at 90 degrees C. and then we should put units here for the hours. So we're going to further write these enthalpies in terms of heat capacities. And we'll pick as our reference temperature 50 degrees C. So the enthalpy here is going to be enthalpy of B at 50 degrees C plus the heat capacity of B times the temperature that is above 50 degrees C. Likewise here, the enthalpy of A will be the enthalpy of A at 50 degrees C plus the heat capacity of A, 90 minus 50. And this enthalpy of B is at 50 degrees. So what we're going to do is make these substitutions into our first law equation here and do some rearranging. So what I've done now is make these substitutions. 190 moles is what's coming in, these enthalpy terms, in terms of heat capacities, multiplied to 15 times 6, so the units here are moles. And of course these enthalpies are joules per mole, so we're going to end up with joules as the terms on both sides. So we can rearrange this because we see we have enthalpy of B at 50 and also the enthalpy of B at 50. So we're going to just rearrange, put them in a simplified form. So here's the rearranged form. All this is just algebra, bringing the heat capacity terms on this side and the enthalpy terms. So 190 enthalpy at 50 degrees minus 100 times enthalpy at 50 degrees. 90 enthalpy of B at 50 degrees C minus 90 enthalpy of A at 50 degrees C. So here we've just rearranged 90 enthalpy of B at 50 minus enthalpy of A at 50 degrees C. Well, this difference is just the heat of reaction per mole at 50 degrees C. In our original problem, we said the heat of reaction is independent of temperature. Heat of reaction times 90 minus this is equal to, now we can solve for the final temperature once we substitute in the heat of reaction. So I've multiplied out the values and now we'll substitute in the heat of reaction given in the problems. And since these values are in joules, then I convert it to 20 kilojoules, negative sign, to 20,000 joules. Remember, this was 90 moles, so that mole units will cancel and everything will be in joules. And so I can just solve now for the final temperature in the reactor. So final temperature minus 50 is 229. For the final temperature, since this is degrees centigrade, 279. And probably realistically, significant figures, 280 degrees C. And so the temperature is increased from 50 degrees C originally in the reactor because of the exothermic reaction and also because we're adding A that's at 90 degrees C. And the thing to remember, we've applied the first law of the energy balance to the reactor, and the heat of reaction term just naturally dropped out from doing the enthalpy terms correctly.